Greetings and welcome to a new video about another mechanical system analysis. This will be our example 6 about a rotational mechanical system. Again, a mass damper and spring combination. But in this case, we'll also see a gearbox in this system. So let's also consider that in great detail. Of course, we will work out the calculation for that and also verify these in MATLAB simulation using Simlink's and Simscape elements in MATLAB. So let's look at our problem for this example. We have this rotational mechanical system with a gear. You can see this in this form. So we have inertia here, so mass. We will apply a torque here, so the input torque. We will also angular displacement here for this part. This rod here has some damping, which will be then clarified in great detail shortly. So there's some damping coefficient. We have a gear part N1 on top, and we have also the gear teeth, the N2 on the bottom. So we have the gearbox in total, which compose of these two elements. Again, we have a rod here, but it has in this case only a torsion modeling, so it's only a rotational spring, and has a coefficient K. And here we have the θ2, which is then the angular displacement for this side. So let's say this is the input side, this is the output side. You can see this, the direction of this rotation is actually in this form. So actually out of the paper or the screen from the bottom to the top, you go in the top in paper or in the screen. But in this case, do the reverse because of this rotation. This part is fixed, so it's a mechanical, let's say the reference part. Okay, in addition, what we see is that inertia, the coefficient of this damping, and also the coefficient of this torsion, rotational torsion is given. So 1 kilograms times meter squared for this for the inertia. The coefficient for the damping and also the coefficient for the rotational torsion is given. We also have the N1 and N2. So we have 30 for N1 and N2 is 60. So we have a ratio of 30 over 60, which is then 0.5, or looking from the outside or the inside, you can also say it is 2. Okay, now we need to, of course, discuss this using lumped elements. So we need for that the inertia, but also, of course, the damper and also the rotational spring. So for that, we can convert this diagram in a mechanical rotational system, which has the components we require. So we have now the inertia, we already had that. Now this rod, which is then modeled by the damping, is now given by this. So it is just a damping with a coefficient of B. We have this part for the gear N1 and N2 for the bottom side, and we have also the outside rod, which is only a torsional rotational part, which is then composed of a spring with a constant with a coefficient of K. And this still is the fixed point for our mechanical system. And again, you can see the input torque. So let me go one by one through these elements. So we have the input torque, T in. We have also the input or the angular displacement at the input side. The inertia J, which is already given. We have the B coefficient, which is then this value. And we have also the gearbox. Now, let me clarify this in detail what's happening here. Because this will be applied, so we will apply a torque here, the part of the gear will respond to that, and that is actually the response torque, which is then called here T1. In addition, because this is in this direction, the T2, which is then the response torque for the N2, this part of the gearbox, will then go in that direction. So this is how you apply your input. That will respond in the opposite direction, and of course this will also go in the opposite direction of this one because it is rotating in that fashion. Now, in a similar form, your rotation of your output angular displacement is still the same, so you can see the θ2 also here. So this is the complete diagram we will use to set up the equations of motion and then go on to other analysis. So let's then see what we require for this situation. We have two questions. Determine the transfer function GS, which is then θ2 over the T in, which is then, let's say, the output angular displacement over the input torque. Okay, just one transfer function. What you also want to have is adjust the gearbox ratio, so this N1 and N2 ratio, to reduce the overshoot in G, in this case, by a factor of 2. So if you have, let's say, 20% overshoot here, we like to reduce it by a factor of 2. That means 10%. Okay, so we need to know then also the overshoot here. That's also one of the objectives. Okay, let's then look at the solutions. First, we start always with the differential equations. Using Newton's second law for rotation in this case, we know this applies for actually each element. So we have then J, which is then the moment of inertia, or just inertia for short, times the second derivative of our angular displacement is equal to the sum of the torques. We already discussed this. Now let's then develop or set up the equations, the differential equations for each gear part. So let's say the gear 1, which is just called this part, and gear 2 will be later on this. So for gear 1 we have this, which is then left side, just the J times the second derivative of the theta 1 is equal to the torque A, because that is in the same direction as the theta, minus this one, because that will oppose this direction of the theta 1, and also minus the damper, because that will also fight back, which is actually also shown here, and it is then B times the first derivative of our angular displacement, or just the angular velocity. So this is the, let's say, the setup and the balance for the part of gear 1. Now in the same fashion you can do it for gear 2, but since there's of course no torque applied, let's say from the, I mean there's no moment of inertia, I must say, for this part, we can just say, okay, that's part 0 is equal to T2, because that goes in the direction, let's say, in this fashion, but the spring will fight that back. That's why we have minus K times the theta 2. So we have now actually the differential equations we require for this, so the gear 1 part and the gear 2 part. Okay, now let's then move on and then transform these in the Laplace domain or the S domain. It will be, of course, much easier to work out the transfer function. So let's do that for gear 1. What we do, we assume the initial conditions are all 0. That means the first derivative give you an S, and the second derivative will give you an S squared. And then you can move on to the third derivative, etc., in the same fashion. And everything gets a S instead of a T, and everything gets also a capital letter instead of a small letter, if there is of course a small letter there. So this part is just the transformation from the time domain to the S domain, the Laplace domain. So you can see the S squared times the theta 1, and the similar fashion for this is just of course one derivative, so you get the S only. Now you can rewrite this so that you have T in is equal to the rest. So you can say T in is equal to this plus all the terms here, of course, and then you get this expression. Okay, that's, let's say, equation number 1. We will use it later. Gear 2. Gear 2, again, a similar form. You only have actually this and that. We just convert that in S instead of T. There are no derivatives, so that's quite easy. Now we can also work out this and say T2 is equal to K times the theta 2, which is quite easy expression. Let's say that's also equation number 2. Okay, we have now 2 equations, and given in Laplace domain for this system, gear 1 and gear 2 parts. Now let's also look at the gearbox equations, because they are important. We have the following equation, which says actually the gear 1, actually the part of here, the rotation, angular displacement, over the angular displacement of this gear 2 is equal to the ratio of N2 over N1. You can also see that is as the following. You can say theta 1 times N1 is equal to theta 2 times N2, and it will give you this expression. Now if you convert that, you can then say, okay, let me then express that theta 1 and the theta 2 and also the rest of the parameters. You will get this equation, which will be then equation number 3. You can of course also write it down as theta 2 is equal to the, let's say, theta 1 times N1 over N2. That's also fine, but that's actually what I have just used to use this later. You also have the relationship for the torques, because we have the torque here, torque 1, and also torque 2, and that has a relationship in this fashion. So the torque 1 over torque 2 is N1 over N2. So If you increase this ratio, let's say, you will increase also this ratio in the same fashion. And you can also rewrite this and you can say, okay, I will have T1 here because that's actually what I require, for example. Then you have the expression as shown here. Quite easy and looks similar to, let's say, the transforms in electric circuits, because those are the across variables and those are the through variables. Okay, now we have the equation number 4. So we have now 4 equations, 2 from the Laplace transform, from the differential equations, and also from the gearbox we get 2 equations in addition. Okay, now let's then move on and then work out this and use these 2 equations in here. So let's then say substitute this expression in this equation number 2. Why? Because we will like to move on towards the Tn and also θ2. That's actually what we want to do. So we will actually get rid of all the terms which are not relevant to this transfer function. So that's what I want to say is first substitute this. You will get θ1 is equal to n1 over n2 times θ2, which is this. Just you get this one. So now you can say this is equation number 5, and then say let's then substitute this equation number 5, the new one, in equation number 1, which is the big one. So the T1 goes in here. Now then we get the following. Tin is equal to this term completely, so n1 over n2 times k times θ2 plus this complete term here. So we haven't changed that. And what you recognize here, the following. It's almost what we want. There's of course the θ1 and θ1 here, so we need to replace that. But we are very close to what we actually want to achieve, because if you want to set up your transfer function, that actually is always the case, you need to set up an equation where you only see the Tn and let's say the θ2 in this case times some coefficients from the system. But you cannot have a T1 or θ1, etc., because that's not what we want. We only want the ratio of these 2 values. Okay, that means we need to also replace this θ1. But we know θ1 is related to θ2 in this fashion. That's actually the reason why I have set up this equation. So if I now do that, and I call this equation number 6, and I can say, okay, let's then substitute this 3 in this equation number 6. What do you get? Straightforward, you get actually this. So n2 over n1 times θ2, similar fashion in this phase. So you can see now we have only Tin and θ2s, exactly what I wanted as my final result. And I call this equation number 7. Okay, now let's move on with that part. This is the equation I need. I can of course move on and then work out this more in detail. I can say, okay, the θ2 and θ2, I have it here. So let's bring these 2 terms together and also take out this n2 over n1. And I have only θ2 here. What I also say is that θ2 is also there, of course. So you can also take out complete thing and say, okay, this term, so n1 over n2 times k plus this, so js squared plus bs quantity times n2 over n1, and the whole thing times θ2. And that's equal to Tin, which is the input torque. Now we are very close to actually what we want, because now I can say, okay, θ2 over the Tin is actually almost visible here. So we can say, okay, θ2 over the torque n is equal to 1 over, which is actually shown here. How can I check this? Because sometimes it is not really easy to see this. You can now cross multiply and see if you get this back. So 1 times Tin is Tin, which is the left side, and the θ2 times this term is exactly what we see here. So this is correct. That is exactly also what we want to have the transfer function. So I have actually now given here this in a little bit larger form. All right, which also see is it's in order now from the highest order to the lowest order. So you get the s squared and s and then some parameter. So interesting is you can see the k from this part, from the outside part, is actually reflected to the input by n1 over n2 squared. So you multiply actually your spring constant by this ratio squared. So if your ratio is, let's say, 0.1, you square that and you will get then 0.01 times k value and reflect that to the input. It's a nice observation. Okay, now we can move on and then say, let's then also substitute the values we have, because we know what we have for this situation, the j and a b and a k and also the n1 and l2. So let's substitute everything. So we get 1, 2 here, and you get also here 16 and then times 30 over 60 squared, and you get in the denominator 30 over 60. So then you get the following, if you simplify this, 0.5 over s squared plus 2s, and this is 1 over 2, so it's 0.5 squared will be 0.25, or 1 over 4 times 16 is a 4. So this is our final transfer function. It's actually the question, or the result for question A. Okay, now let's move on and work out this in great detail further. We have the second order model without any zeros or delay. This is the model for our second order system if you don't have any zeros or any delays. Now we have several parameters here. We have the steady state gain, which is called the KDC. We have the natural radian frequency in radians per second, which is then omega n. And we have also the damping ratio, which is related to the overshoot, but also to the settling time and also to other parameters like the rise time, etc. So we have this. We already determined that. So we know 0.5 over s squared plus 2s plus 4. So how can we then recognize our parameters as KDC, omega, n, and zeta? Just compare the terms. So compare the terms in this model H with this system we have set up. So it's quite easy, just straightforward business. You do actually omega n squared at 4. That means omega n itself then square root of 4 is 2 radians per second. That's simple. Now we get 2 times zeta times omega n, or the first one, let me do it first, this KDC times omega n squared is actually 0.5. That means KDC is then 0.5 over the omega n squared, which is 4, so we get then 0.5 over 4 is 1 over 8, or 0.125. That's for that part. And the final one is there's 2 times zeta times omega n, which is then 2. So this part, which is then of course the coefficient of the s, is 2. Now I can say I want to also have the zeta because I have the rest. So that's the final one. Zeta is then 2 over this 2 times the omega n. I have the omega n, which is 2. So 2 over 2 times 2, which is then 1 over 2, 0.5. So I have now everything, which I require also for my, let's say, the overshoot calculation. Now let's look at the performance of our system G. Let's look at the overshoot first. This is the formula we can use for the overshoot. You can see this exponential expression. You can see the MP, which is the overshoot, as a scalar value, is e to the power minus pi zeta over 1, the square root of 1 minus the zeta squared. So if you just substitute everything, just of course zeta, 0.5, you will get very close to 0.16 or 0.163, so 16.3%. We will verify this later in MATLAB also. So this is the situation for this system using these values. Okay, let's also look at the settling time, just as an extra information. Settling time is given by this approximate expression, which is not an exact expression for the second order. By the way, this is an exact, but this isn't. So it can be that your system have a little bit more, a little bit less settling time. Okay, that's then 4 over zeta times omega n. We know the zeta and we also know the omega n. So if I now substitute everything, I will get 4 seconds. So I expect close to 4 seconds for my settling time. You can also calculate the peak time and also the rise time and also other things. We also know here, if I look at it, the steady state value is 1 over 8, but you can also look at it from here. You can say if I substitute in here s is equal to 0, this will go, so s will go because it's 0 squared, and this is then 2 times 0, so it's gone. 0.5 over 4, it is again 1 over 8, so you can also see that from that expression. Okay, let's check this later also in the simulation. Now, the second part is we will like to reduce the overshoot by a factor of 2. That means the new overshoot must be then 0.163 over 2. That is then 0.0815 or 8.15%. That means I keep these values for my inertia, for my damping coefficient, also the torsion, the spring constant. But I can change my N1 and N2. That's also what the question was. So adjust your gearbox ratio in order to have overshoot, which is then reduced by a factor of 2. Okay, I need this. And the new damping ratio will be then given by this expression. This is just worked out form from that exponential expression from the MP. We know the MP was given by e to the power minus pi zeta over the square root of 1 minus the zeta squared. If you work that out, so express actually everything in MPs, so the zeta is then given by this expression. MP must be substituted in here using a scalar value, not this percentage. Now, if I now do that with the new overshoot, I will get 0.624. We had 0.5, so we go up. That means if you go up with your, or increase your damping ratio, your overshoot will decrease. Okay, now the expression we had in general for this system was this. We now can substitute everything we have except, of course, this N1 and N2 ratio. So that's actually shown here. So what I have is then this one. And I can now say, okay, this is the second order model. We all know this. Now this we have, again, this. And we now, since the zeta is now 0.624, the omega n is also changing because it was 2, now it is 1.6 approximately radians per second. Now the omega n is then given by this, because now you can compare the omega n squared is this. Now that means I have to now also calculate N1 over N2, which is then of course what we require for this question. Now if I now also take the square root of the left side and the right hand side, I will get N1 over N2 is omega n over 4. Okay, that's a nice result. That means I have the omega n over 4 will give you approximately 0.4, because it's approximately 1.6 over 4 is 0.4. So I have my my ratio. It was 0.5 before because it was 30 and 60. Now it is decreased and it will be now 0.4. It doesn't matter, of course, which values you take here, if there is of course a ratio of 0.4. So you can of course take 10 here and 40 there, or 60, keep it 60 this one and then change that one such that you have that 0.4. That's actually really the business here. Okay, now selecting this, again I said, okay, let's keep that N2 because I only want to change one part of the gearbox. And I can of course do then N1 as 24, because 24 over the 60 is 0.4. Many other possibilities are fine. This is just one of them. Okay, now having also determined the N1 over N2, we can now substitute this value in here and also in here. Now we get 0.4 over s squared plus 2s, that doesn't change, plus 0.4 squared times 16, that will give you 2.56 here. Now that's now our new expression. We had before 0.5 over s squared plus 2s plus 4, so it has changed because the overshoot must be reduced by a factor of 2. Did we know that before? You cannot just recognize that by looking at it. You need to work out this step by step in order to have this new transfer function. So this is the new transfer function for this new overshoot specification. If you have other specification, this will change. Okay, let's then check the mechanical system in Simulink using Simscape elements. This is what I have set up. So this is the setup step input torque, which is then 10 Newton meters in this case. I have an what's called the Simulink signal to physical signal converter. So this green part is completely the mechanical domain. So this part outside in black is the Simulink business, Simulink signals. We have this torque source, so it will then apply that torque here. We have the inertia, we have this rotational damper, and then we have this gearbox. It is a very simple gearbox without any losses, etc. No backslash, nothing, only that ratio. And then we have this rotational spring, and we measure, of course, here the motion. So that's actually what we have, an ideal rotational motion sensor. That goes in here. We measure only the angular displacement, not the velocity. that goes also here. And we also now need to convert that mechanical signal to the Simulink signal. So that's actually what's also shown here, physical to signal to the Simulink signal converter. We have a scope that will plot that angular displacement out and also the torque in. So we have now two displays. And this is required for our reference as, let's say, the ground in electric circuits. This is the mechanical reference for rotational systems. You can see this C is then connected there because it was also connected to the mechanical reference at the spring. And everything is measured according to that reference. So you can also see that the ideal rotational motion sensor is also a reference to that. So, and we have a solver here to solve that whole business. Now we have here again the values: inertia 1 kilograms times the meter squared, damping coefficient, the spring constant, and also the gear ratio, which is then from B to F. So it is going from here to there, which is then 30 over 60, 0.5. It's also shown here. That's of course the initial situation. Okay, now let's then look at the response of this in Simulink. This is what we get. So you can see this input torque is 10. You can go up by 10 Newton meters, and stays there forever. And this is the green one is the response. So and this the measurement is actually shown here. So you can also recognize this here. So at 1.8 seconds we get 1.45 radians. That's our displacement, the maximum. But if you wait long enough, I can of course also give you the peak value and the peak time. But if you wait long enough, the steady state value will be then 1.25 radians. So we have now the information from this plot. What does it mean? Now from the calculations we know that overshoot was 0.163 or 16.3%. Now steady state value was in our case 1 over 8 or 0.125, but we have of course now input of 10, so it will go up by 10 times. So we have now 10 times that 0.125 will be then 1.25. So again, that confirms our calculations, this simulation result. And we have the MP calculation. Just looking at the simulation data, we can say, okay, the theta max, which is then of course the maximum value for this output angular displacement, is 1.45 minus this steady state value over the steady state value is 0.16. Now very close to that what we have calculated. So this confirms again our calculations. So that's good. Okay, now let's also look at the code I have used for MATLAB. This is a code I have used. This is the part for the next for the part B, in order to have the reduction of the overshoot by a factor of 2. You can see all the values in N1 and N2, transfer functions, etc., and all the rest of the situation. So you can also try it out by using this script. Now, in order to check that also in MATLAB, I also plotted the response in MATLAB. So the torque is again 10. The gearbox ratio is again shown here, and I have now set up this equation, this plot, and you get this response. You can see this overshoot is 16.3, so exactly as we have calculated, at the same amplitude value, peak value, and also the same peak time. So that's really nice. The setting time, we get more information actually here, is 4.04. Now close to what we have discussed and also calculated. I already said the equation for the setting time, this 4 over that zeta times omega n, is an approximation. It can be that your system is a little bit, will have a little bit larger, a little bit smaller setting time. In this case, it is a little bit larger, but very close to what we have. You can also see the steady state value, the final value is 1.25. Again, 10 times that 1 over 8 is what we have here, because the 10 times is due to that input value. So that's all nice. And the calculations again was this, and you can see they really match the simulation results. That's really nice. Okay, so we have now the part A done, and we have verified everything using the Simulink and also the MATLAB script using this and having the step response. Let's also again set up the mechanical system and then just adjust ratio. So nothing is changing except this 24 instead of 30. Everything is the same. Okay. Again, this physical to Simulink to physical system converter, and the reverse is here. Now I get a response for the angular displacement in Simulink, as this value, and it's a little surprising for me, so I just wanted to show you this. I've actually tried to manage this, but somehow I get this result, but I will discuss this also in MATLAB. So what you see is a step input again, torque of 10 Newton meters. These are the results. And what's now surprising is the following. The peak value is 1.96 radians at this peak time. So the peak time is changing. But okay, these are the values again. And this is steady state values, is 1.56 radians. What's interesting is if you now look at the requirements, this was requirements, right? So it's actually the new overshoot for question B. It was 8.15%. Now look at the simulation using this. The maximum is 1.96. It's also shown here, so you can see, and also the steady state value is 1.56. Over 1.56 is then 0.256, then 25.6%. It's actually going up. So something strange is happening. So I've tried to fix this, but I was not able to manage the response in Simulink using the Simscape elements and to get the exact result I wanted. I was successful in doing that using the script I have shown you a couple of slides ago in just MATLAB command window. But this is strange. So if you know the reason, please let me know. But I just want to mention this in order to also discuss this in the comment section with you. And maybe you have a solution that will also help me in later analysis. So something is happening here and I don't know what. Now, no matter, we can always check that in the MATLAB, and this is now the Y new. And again, with this ratio, torque is still the same. And you can now see that indeed the overshoot is 8.08. And it is now 8.15, of course, we want, so it is close. And this is now the peak time, and also the values are shown here. You can also see the final value is 1.56, so that's actually exactly as we have in the Simulink, but this is quite different actually. So that's again my problem. And the setting time is also close to 4, and again the final value. These are the calculations, so the setting time is what we have here, but this is what we get from simulation, so it gets close. Now, this is promising, so we can say it is confirmed. Again, the overshoot in Simulink simulation was much higher, so that's something happening there. We don't know yet what it is. So this confirms now the situation. We have now managed to reduce the overshoot by a factor of 2, at least by a factor of 2 in this case, by just adjusting the gear ratio. So going from 0.5 to 0.4 in the second case. All right, this is then for this example about the mechanical system, rotational mechanical system, showing you how to calculate the overshoot and of course other parameters like the settling time, but also how you then can adjust your overshoot by just looking at the gear ratio. That is most of the time also much practical to adjust instead of your inertia or something else, because it is something a part of your system. So the gear is something you can add, but the damping ratio or the coefficient or the torsional rotational spring coefficient is not what you have actually in hand. You cannot just adjust that easily. All right, if you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people. Thanks for your cooperation and see you next time in another interesting video. Take care.